Hello everyone, in this video we are going to solve the reaction kinetics of a PFR with a first order reaction. Now PFR is known as a plug flow reactor. And it's called a plug flow reactor because our flow is fast enough that we get essentially plug flow. So it's basically a constant fluid velocity throughout this pipe. And throughout the pipe, this reaction, A goes to B, is happening as we go along the length of that pipe. We're going to assume we have first order reaction kinetics. We're also going to assume this is an isothermal reaction. And we're also going to assume that this is a liquid phase PFR. Often PFRs are run in the gas phase, and that can be challenging, especially if you have a change in the number of moles as you go from the reactants to the products. That makes it a little bit more complicated. Come back to another video in the future for that problem. To solve this problem, we're going to start with a mole balance. So we're going to write dN dt, and we're going to look at our species A in this reactor, and that's going to be the species for our mole balance. So dNA dt is equal to what goes in minus what comes out plus a generation term. This is the reaction term for our reaction. And even though it's called generation here, this is going to be consumed throughout the reaction, so this generation term is going to be negative. And we could look at this whole reactor altogether, but actually we're going to look at a subset of this reactor. So imagine we have a cross section right here. And this small control volume is where we're going to look at this reactor. We're going to label this first point as V. This is as if we've traversed a certain amount of volume in the reactor to get to this point V. And then this gap here is going to be called delta V. So we have this point right here is V plus delta V. A small change in volume. How does that change the reactants and products? So we're going to look at what comes in and what comes out. So this in term is going to be our molar flow rate of A. That's our species A. And the out term is going to be molar flow rate at A as well. But here, this first one is going to be evaluated at the point V, at this area right here. And our out term is going to be at V plus delta V. So again, that is this location right here, the second part of our control volume. Our generation is going to be our rate of reaction RA times the volume of this small control element right here. And so that's going to be delta V. Since the PFR is run at steady state, our dNA dt within this control volume is going to be equal to 0. There's no accumulation within that control volume, so we have 0. And now we can solve this equation to set up our PFR design equation. So what I'm going to do is bring some of these terms over here to the other side of the equation. So we have FA evaluated at V plus delta V minus FA evaluated at V is going to be equal to RA times delta V. And next I'm going to divide by delta V to solve for RA. So we get FA at V plus delta V minus FA at V divided by delta V is equal to our rate of reaction. Now this term right here may look familiar. This shows up in a lot of chemical engineering type problems. If you think back to calculus, this may seem similar to a definition of a derivative in calculus. So the definition of derivative is f of x plus some delta x minus f of x divided by delta x. If we take the limit of this as delta x goes to 0, this is equal to our derivative df dx. So what we need to do here is take the limit as delta v goes to 0, and then this can turn into a derivative. We have f of a evaluated at v plus delta v minus f of a evaluated at v. That gives us dfa dv is equal to RA. And this is one form of the design equation for a PFR. We're going to think about this problem in terms of conversion of A to B, and we're going to call that variable x. So x is equal to the number of moles of A that have reacted divided by the number of moles of A fed to the reactor. And in our PFR, we can think about it like this. At that starting point, when we just enter the pipe, we have pure A. And so our conversion X is going to be equal to 0. No moles of A have reacted in this fraction here. Whereas as we progress down the reactor, more of A has been converted to B. So now we have A and B. And so our X is going to be increasing as we go down the length of this reactor. And what we want to find out is that at a certain point in the reactor, or maybe at the outlet of the reactor, what is the conversion? That's what we're going to solve in this problem. To do that, we need to find a way to get conversion into this differential equation. And so we can use that in terms of our flow rate. So if we can write X in terms of that flow rate, we can plug it into this equation. The number of moles of A fed to the reactor is going to be equal to FA0. That's our starting inlet concentration of A. And the number of moles of A reacted is going to be equal to FA0 minus FA. And so this FA here is the molar flow rate at a certain point in the reactor, and FA0 is going to be the molar flow rate at the inlet of that reactor. So what we can do is now write X is equal to FA0 minus FA over FA0. And then we want to plug that into this equation right here for FA. So we need to solve this equation down here for FA. And we end up with FA is equal to FA0 times the quantity 1 minus X. Now that we have our design equation right here and this equation for flow rates in terms of conversion, let's try to solve for a differential equation in terms of conversion. So if we plug this in, dFA0 times 1 minus X dV. First, this term FA0 comes out of the derivative, so we get FA0. And then now we have to take the derivative of this interior part, 1 minus X. The derivative of 1 goes away, that's 0. And then this negative sign sticks with the X, so that'll come out of the derivative as well. So we have a minus sign here. And then we're left with X, which does change as you go through the reactor, dV. And what this derivative here means is that this is looking at what is the change in our conversion as we traverse some length of our reactor V. So meaning as we go down this reactor and say we take a small step from this point to this point, how does our conversion X change? And this is equal to the rate of reaction RA. Now in this problem, we set that RA is equal to negative K times the concentration of A. We can rewrite this equation, negative FA0 dx dV is equal to negative K Ca. And now we know what things change here. Our FA0 is a constant, our K, our reaction rate constant, is also a constant. And so the changing terms here are our X and our Ca. So in order to solve this problem, we need to write Ca in terms of X. We can do that with a similar approach that we used right here. If we take this equation and divide by the volumetric flow rate of the reactor, we can write a similar expression here. Ca is equal to Ca0 times 1 minus X, and we can plug that in to this term right here. So this is equal to negative K Ca0 times 1 minus X. We're now ready to solve this differential equation. I'm going to move all the terms involving X to one side of the equation and then everything else to the other side. So first let's cancel out these negative signs. We have dx divided by 1 minus X is equal to KCA0 divided by FA0 times our dV. We can simplify the right-hand side of the equation a little bit by noting that the relationship between FA0 and CA0, so FA0 is equal to little v naught, this is our volumetric flow rate, times our CA0. If we substitute in, we can cancel out these CA0s eventually, and we get K over our little v0, this is not our big V, times our change in volume. And I'll call this a capital V just to make it clear this is different from our v0. And now we can integrate these equations. So I can take the integral of both sides. We're going to integrate from some value of V equals 0 to some other V at the end of the reactor. And we're integrating from 0 to some value of x. Now this integral looks like a 1 over x, but we have a negative sign here. So this is going to evaluate to negative when we pull out this negative sign, ln of 1 minus x. And we're evaluating this from 0 to x. So that's equal to negative ln 1 minus x by plugging in for this top part of the integral. And then now when we plug in the bottom part of this integral, we get ln of 1, which is just 0. So this is all we have, minus 0. That's the left-hand side of this equation. And the right-hand side of this equation, right here, we can just evaluate this. dv, these are just constants. So that gives us k over little v0 times our capital V, or volume of the reactor at that point through the PFR. So putting this all together, we get negative ln of 1 minus x is equal to k over little v, our volumetric flow rate, times our volume of the reactor. I'm going to solve this equation for our conversion x. So first let's multiply by negative 1 and then take the exponential of both sides. So we get 1 minus x on the left-hand side is equal to our exponential of negative k over little v0 times our volume. And then to solve for x, we can get this is equal to 1 minus the exponential of k over little v0 times our big V. So let's quick think about what this means, because this might be a little bit counterintuitive, at least it was for me at first. Now imagine this is our PFR, and it'll extend out as long as it goes. In this equation, we have our conversion as a function of our volumetric flow rate, our rate of reaction, and our volume of reactor. And usually we're used to thinking about our volume as being a constant. That's just how big the reactor is. But in this case, it's how far along the reactor we have traversed. So let's say that we have gone this distance through our reactor. We've traversed some volume V. And at this volume V, when we've made it this far, let's say this is 5 liters, then we can plug that into this equation here and figure out what is our conversion x at 5 liters. And then let's say we get down to this point in our reaction to some new V, call it V prime. We can plug that into our equation and then figure out what our new value of x is. And then as we go further and further along in the reaction, we're increasing that value of our conversion. And it follows this exponential trend. We can make a quick plot. So imagine here again is our reactor, and here is our plot down below. This is our volume, and here on the vertical axis is our conversion. We have 0 and we have 1 right here. We start out when V equals 0, x equals 0. Imagine you plug in V equals 0 here. This exponential term turns into 1, and 1 minus 1 gives you 0. So that's why we start out here at 0. And then we approach this value of 1 exponentially. And eventually we asymptotically approach 1, never quite getting to 1 until V goes to infinity. When V equals infinity, then this exponential term will go to 0. And then finally our conversion reaches a value of 1. To summarize, in this problem we had a PFR and we looked at a first order reaction within this PFR. We solved a mole balance, used this to derive a design equation for that PFR, and eventually solved for our conversion x as a function of our constants for this problem and our volume of the reactor as we progress through that PFR. If you want some practice, you can try to solve this again, but using a different reaction rate order, or you can try to solve it without going to conversion and just doing it in terms of the molar flow rates or the concentration of species throughout this reactor. I hope you enjoyed this video. Thanks for watching.